Hi students, this is the review for Spiral 9. We're going to start off with unit circle trigonometry, and the goal for these is to find the exact trig values. The first thing we're always going to have to do is to identify what family these angles are in. So for example, the first one would be pi over 4 family, second one is going to be pi over 6, third is going to be pi over 3, pi over 2, I skipped one, hey, it's the same number anyway, and then pi over 6. The next thing we've got to do is to identify where in our unit circle these things are. For cosine of negative 19 pi over 4, well, that's like saying we're looking at negative 4 pi because we've got 4 pieces here, and then we've got minus 3 pi over 4 more. The reason that I want to talk about that way is to say, okay, well, there's 2 pi, 3, 4 pi, and then we've got to go 3/4 of 1 pi around again, which is going to take us to right here. Here we've got negative x and negative y. All right. Cosine of pi over 4 is going to be the square root of 2 over 2. For that, we're going to use our x value. Here it should be negative. So cosine of negative 19 pi over 4 is going to be negative the square root of 2 over 2. For the second one, doing the same thing. Cosecant is going to be the reciprocal of sine. So I'm going to find sine of pi over 6 first, and that's going to be a value of 1/2. All right, so I'm going to use that to find cosecant in just a minute. Now I've got to figure out 11 pi over 6. That's not a full circle. It's a little bit less than 2 pi. So I'm thinking about this as going around not quite a full rotation. I'm in quadrant 1, so this is going to be a positive value. So cosecant of negative 11 pi over 6, whenever I have 11, I always draw them as pi's, and that annoys me because then I need to scroll things out, is going to be the same thing as sine of pi over 6, the reciprocal of sine of pi over 6. I forgot a really important word in that, which is 2 over 1, or 2. For cotangent, it's the reciprocal of tangent. You might also recognize that this is going to be a value of x over y. So if I can figure out what the coordinates are there, I'm in good shape. In terms of where on the circle this is, we're dealing with 3. So I might think about this as 2 pi is going to be 6 pi over 3. And if I wanted to think about this as going around 2 full times, that would be 12 pi over 3. But then we'd have to go back 1. So what if I thought about this as negative 12 pi over 3, which would be going around 2 full times, and then plus 1 pi over 3. Let's see where that would end up. So we're going around 2 full times backwards, 1, 2, and then have to go positive pi over 3. So we're in the first quadrant. That's kind of nice. My coordinates here would be 1/2 comma root 3 over 2. And if we're talking about this as x over y, that would be 1/2 divided by root 3 over 2, which is going to give us 1 over the square root of 3 as our final answer. For 9 pi over 2, as soon as I see that pi over 2, I just need to decide if it's the top or the bottom. And to do that, I want to think about this as, okay, this is 1/2, 3/2. Then I skip into 5/2, and then 7/2, and then 9/2. So that's going to be a top value, which is 0, 1. And cosecant goes with sine because it's the wrong letter. I need the y value. This is going to be a value of 1 because the reciprocal of 1 is 1. Hey, look, we've got another one that's basically the same problem that we just did, But now we're going around backwards. So that would be 1/2, 3/2, 5/2. That'd be 0, -1. Cosecant goes with sine, so that's my y value. And -1, the reciprocal of itself is -1. So we end up at -1 for our value. For the last one, we've got cosine of -13 pi over 6. So I'm going around one full cycle. That would give me to 12 pi over 6. And then a little bit more. We're down in quadrant 4. Thinking about this, we've got an x value that is bigger, so that's going to be √3 over 2, and that's positive. And my y value is going to be -1/2. For cosine, I care about the x. My answer is the square root of 3 over 2. Next up, we've got to do some graphing of trig stuff. I'm probably going to run out of room here, but I'll do the best that I can. I'm going to draw my axes first. I've got a midline at -1. So I'm going to draw that. Cool. I'm going to go up 4 and down 4 from there. So there's 3. And here is -5. Those are my amplitude lines. I like drawing those in as well, as you know. Then we have our starting and ending points. So I'm going to do 2. I'm just going to write it in x instead of theta. Minus 7 pi over 4 is equal to 0. That means that 2x equals 7 pi over 4, and x is equal to 7 pi over 8. That's going to be like here, just, for funsies. And I'm going to have an end value at 2x minus 7 pi over 4 is equal to 2 pi. That would be 8 pi over 4, so if I add 7 pi over 4 to the other side, that's going to give me 15 pi over 4. Dividing by 2 gives me 15 pi over 8. I'm going to put that somewhere here-ish. I don't know why I extended that, but I did. All right, I know cosine, if it's positive, should look like this, where I have my beginning and end points at the top. Exactly in the middle of these two, and going from 7 to 15, 11 pi over 8 is going to be in the middle. And then I'm doing the same thing, going exactly between these two. Between 7 and 11, we've got 9 pi over 8. That's going to be a midline point. And between 11 and 15, that's going to be 13 pi over 8 on the midline. Nice smooth curves, so we go down, back up, and more back up. And that's it. For the next one, I'm basically going to do the same thing. The problem that I've got is I've got cotangent. So that plays some games with some of the things that we're comfortable with. I'm going to start out by beginning this process again. And thinking about this, I'm going to first find my midline, which is at -1. And then I'm going to do the same thing that I did before for dealing with the beginning and the end. But instead of 0 and 2 pi, I'm going to use 0 and pi. Because those are places that I may have to deal with either asymptotes or zeros. And I always have to think about this for a moment for cotangent. So we're talking about the point 1, 0 here. Cotangent is x over y. So that means that this is going to be an asymptote because we'd be dividing by 0. All right, the other thing that we can get from this is that we can go up 1/2 and down 1/2, and that's going to be where our next points are. Although for cotangent and tangent, I don't care about those so much. I care a lot more about these asymptotes. So let's find these asymptotes. So we've got, change this to x over 2 plus 11, see I did the same thing with the 11s, 11 pi over 6 is equal to 0. Moving that to the other side, multiplying by 2, I get x is equal to -11 pi over 3. I didn't do it that time. Yes. And that's going to be our first asymptote. So negative 11 pi over 3. And we've got an asymptote going through there. Cool. Then we're going to do the same thing for pi. I don't have a heck of a lot of room, so I'm just going to kind of do this in my head. So that would be 12 pi over 6. If I subtract it to the other side, I've got 1 pi over 6 times 2 would be pi over 3. So I'm going to put that, I don't know, maybe here. And we've got a nice asymptote there as well. Exactly between these two places is going to be our midline point. And if I'm talking about between negative 11 and positive 1, that's going to be at negative 5 over 3. And my midline point, I made that purple, should look something like this. All right, and then the last piece is to figure out where this graph is going. And for cotangent, I'm going to plug in a point 0 because that's going to be along the y-axis. I figured that might be worthwhile doing. And I get 11 pi over 6. If I think about that, cotangent of 11 pi over 6 would be somewhere that's down here. And down here, cotangent would be negative. So at this place, we should be below the midline. That means our graph is going to look something like this. And exactly halfway between, we'd hit those points. Again, I don't really care about those. I care much more about the shape. If you want to memorize the shape of tangent is this shaped and cotangent is this shaped, that's totally fine. If you want to use the method I just did, was to plug a point in to see where that should go, that's okay too. I'm going to do these in reverse order, just so we have the graph of sine to help us with one of the reciprocal ones. We know that sine is going to look like this, and I'm going to add some points to my graph now. So I'll put that down here so I have some room. We're going to have positive 1 as my midline. I'm going to go up 3 to 4. That's going to be my vertical place. I'm going to go down 1, 2, 3 to negative 2. That's going to be the bottom of my amplitude. Okay, let's find our starting and ending points. So we've got 3x plus 11 pi over 6. I'm going to minus that to the other side, divide by 3, and I so delightfully get negative 11 pi over 18. Wow, thanks, math. And that's going to go on my midline. So negative 11 pi over 18. Cool. Cool, cool, cool. Doing the same thing on the other side. We've got 3x plus 11 pi over 6 is equal to 2 pi. We know that's 12 pi over 6. So that would really be 3x is equal to 1 pi over 6, which means we get an ending point of 1 pi over 18 for our cycle. And again, that's going to be on the midline as well. So we're going to go there. All right, exactly between those two. And negative 11, positive 1, that's going to be negative 5. I feel like we just did one that had these same numbers, but not over 18. I like how I wrote 15 as I started to write 18. Woof. All the Freudian slips today. That's also going to be in the middle. Let's go for the upper and lower points. Between negative 11 and negative 5 is going to be negative 8 pi over 18. I'm not going to bother reducing that. That's going to be up top. Between negative 5 and positive 1 is going to be negative 2 pi over 18. Again, not going to bother reducing that. And that's going to be on the bottom, which totally lines up on my graph, giving us a nice sine curve that looks something like this. Okay, for secant, I'm going to graph cosine and then make those U-shaped things flipped over. So let's do the same thing. Okay, we've got a plus 0 at the end. So my x-axis is my midline. That's kind of nice. We've got up a half and down a half for our points. I'd like to remind us that cosine should look something like this. So do the same thing we always do. We've got 2x plus 7 pi over 4 is equal to 0. Move it to the other side, divide by 2, and we've got x. I'm going to not do this here because my graph is going to end up there. I'll do this down below. So I've got x is equal to negative 7 pi over 4 divided by 2, so negative 7 pi over 8. Negative 7 pi over 8. Okay, that's going to be an important point. Then we're going to do the same thing for the ending. So we've got 2x plus 7 pi over 4 is equal to 2 pi, which I could write as 8 pi over 4. And when we do that, we've got 2x equal to pi over 4. X is pi over 8. This graph is going to be pretty special in terms of scale. But the nice thing about being digital is that I can make this less painful for me to look at by getting rid of that y-axis and maybe putting that somewhere else. Like, I don't know, close to 1/8 instead of close to negative 7/8. Who knows? Okay, so we've got our values here. We've got our amplitude points. And we know that for cosine, we start at the top, we end at the top. Exactly between these two would be negative 3 pi over 8, which is going to be the bottom. And the midline points would be exactly between those. So we're going to look like something that looks wonderfully like this, except we're graphing secant. And for secant, wherever we have a midline point, that's where we're going to have asymptotes. And for secant, whenever we have a max or min, we have a u that goes on our graph, so we end up looking something like this. The graph of the secant is just the yellow parts, so we don't have to worry about the cosine part of this once we have those in. You don't have to erase yours on your spirals. Next up, we got to do some trig models, and we've got to collect information from data, in this case in a paragraph, and figure out what these things mean. So I see average depth of water. I'm going to assume this is a trig function just because of where this is located. So the average depth of water, that sounds like midline to me. So I'm going to say that's 6. Varies 2 feet in both directions, so it goes up 2 and down 2. That's my amplitude. And there's a high tide at 4 a.m. So this is a max. If the tide goes from low to high every 6 hours, okay, so we have to know something about tides, that this is always going to be equal. So it's going to go up and then back down and then up and then back down every 6 hours. So we're looking at something like this. We've got 4 a.m., we've got a high tide. 6 hours later, we're going to have a low tide. That's going to be at 10. 6 hours later, I'm going to use 24-hour time. That's going to be 16 o'clock, 4 p.m. And that's going to be another high there. The reason that we do this is so that we can say something like, okay, we've got 12 hours for the period. That's how long it takes for a full cycle. And if you know about tides, we live in a part of the world where you might. That makes sense. So we did that. Write a cosine function. Yes, cosine is easier. In describing the depth of the water, t equals 4 corresponding to 4 a.m. That works out pretty well. And then we're asked, when is this at 5 feet? I'm just going to do that graphically instead of kind of do that all out. So we're thinking about this as a function where we have, I'm going to try to color code this, amplitude times cosine 2 pi over the period, x minus, I didn't use that, phase shift. That's going to be wherever our max is. Hey, look, that's at 4. And then that was yellow. We've got plus the midline. So in terms of this equation, we're going to have 2 cosine 2 pi over 12 for the period, x minus 4 for the phase shift, and then plus 6. That would do that for us. We're being asked to figure out where this is at 5 feet. You could plot this on Desmos and get that answer pretty quickly. All right, here's another one. We're tying a weight to the minute hand of the clock. This is varying in a periodic way so that we can actually test this. This is taken from Khan Academy. A lot of their problems are similar to this. They actually have really good problems for this section. But I wanted to talk about a couple of these. Okay, I've also need to figure out that the clock in moving around on the minute hand, looks like everything is in minutes. We're going to have a period of 60 minutes just because we know that this is how long it takes a minute hand to go around. The torque peaks, so we're talking about torque here, 15 minutes after each whole hour. So if we thought about t equals 0, t equals 15 would be the max, and the minute hand pointing directly to the right. Okay. At 3 Newton meters, so that's what the unit we use for torque. So that's like the height of that. The minimum torque at -3 Newton meters occurs 15 minutes before the whole hour. So when we're at the 45 instead of 15. So we got to find a formula for torque here. And I've got to use the stuff that we're given. So we know the period is going to be 60, so I'm going to put that in 2 pi over 60. We've got x minus our max value, so that's going to be 15. And I like using cosine because that lets us use the max and min. I'd like you to notice that we've got a max and a min, 3 and -3. The midline between those would be 0. And if we're talking about how far apart that is from 0, that would end up being 3. We kind of fall into this equation pretty quickly by doing this. I think we got one last one of these, which we are using a sine function instead of cosine. We're told on day 0, the stock has its average value of 3.47. So that's my midline. All right. We also know that if the average is the sine function here, we're talking about this in terms of our midline. So we've got an x minus, I was about to put that, 0 for the time that that happens. All right, then we got one more piece, which is that we've got sine out front. I like that we didn't even need the phase shift here because we're told it doesn't have one. And then we're told that 91.25 days later, the value is down to its minimum. So we've gone from a midline, and then it goes down to its minimum 91.25 days later. What I'd like us to notice is that if this thing is sinusoidal, that means that we're going to have 2, 3, 4 more of those things. So that times 4 would be our period. So that's going to be 360 plus 5. Oh, look, that's like a year. And we end up with 2 pi over 365. All right, last piece is we need an amplitude. And if we think about this, if we've got a max of 3.47, we've got a min of 1.97, the average of these two would end up being our amplitude. So if you're feeling especially lazy, you could write that as 3.47 plus 1.97 divided by 2. I also like how I did the... Oh man, I totally messed this up because this is not the max. 3.47 is the midline. Whew. So instead of that, I just care about how far this is from 3.97. But I can't talk today. 3.47, not 3.97, but 1.97. So that's going to be somewhere on the order of 1.5. Yeah, it's exactly 1.5. Yay! And finally, on to some identities. We're looking at the first one, cosecant squared plus secant squared. Let us try to write these in terms of sine and cosine and see if that helps us. That's going to give us 1 over sine squared x plus 1 over cosine squared x. I'm just going to do this horizontally so I have enough room. I've got to find some common denominators, so that would end up being cosine squared x over cosine squared x sine squared x plus sine squared x over sine squared x cosine squared x. I multiplied each of those by the opposite denominator, and that gives me cosine squared plus sine squared on top. That should be a nice sign for you. And cosine squared x sine squared x on the bottom. On top, that's going to be 1, so 1 over cosine squared x sine squared x, and I notice I'm trying to get cosine on the bottom, cosecant on top. I could rewrite this with sine squared as 1 over cosecant squared x, which would leave me with cosecant squared x on top and cosine squared on the bottom, which is what we're looking for. For the other one of these, we've got cosecant squared minus cosine secant is equal to cosine squared over sine squared. Okay, let's see what's going on there. All right, cosecant squared, that's 1 over sine squared. Already looking pretty good to me, because that gets me something in the denominator. Cosecant, and then we've got secant, cosine and secant, those are reciprocals. So I could write this as cosine x times 1 over cosine x, which is just 1. So we've got 1 over sine squared x minus 1 is equal to something. I could do some common denominator work here again, and that's going to give me 1 sine squared x on the bottom. And then we're going to have 1 being sine squared over sine squared, so it's 1 minus sine squared x over sine squared x on the top. Cool. That's the same thing as cosine squared of x. And we've already got sine squared of x. That's what we were trying to do at the beginning. And that's it. All right, next up, I've got some cotangent stuff that's squared. In fact, in both of these, I've got some weird things going on. It might be useful for me to think about some Pythagorean identity. All right, so I know that I've got a few different Pythagorean identities, one of which is going to be cotangent squared x plus 1 is equal to, this should be cosecant squared x. And that's exactly what I have on the bottom here. So I could rewrite this as 1 over cosecant squared of x. And then I noticed that the stuff on the right doesn't quite look like this. I'm going to have to do some careful trickiness to try to make this stuff work, because what I have right now, 1 over cosecant squared, which is the same as sine squared of x, but I'm missing the secant and cosine. What I'm going to do is going to be kind of weird. I'm going to multiply this by cosine of x over cosine of x. That's just one. It's something I could do. I'm going to separate that out. So this becomes sine squared x times cosine x times 1 over cosine x. And then 1 over cosine x is the same as secant of x. So looking at this, we have all of these pieces in a slightly different order, but that's okay. For the next one here, we've got what looks to me like the messier stuff on the left side of this. And I'm going to rewrite this as 1 over sine squared x plus 1 over cosine squared x. And if you're saying this looks a heck of a lot like the first identity that we did a few minutes ago, you're right. We're going to find a common denominator for the bottom. So that's going to be something like cosine squared x plus sine squared x over sine squared x cosine squared x. I did that same step a few minutes ago, so if you want to go back and watch that video part again to help, that might be useful. And when I do this, I could rewrite this as 1 divided by cosine squared plus sine squared is 1. And then we're going to have sine squared x cosine squared x. Dividing is the same thing as multiplying by its reciprocal, which is sine squared x cosine squared x as our final value there. And that's what we're trying to get. All right, last set of identities. And I'm going to start by writing these things in terms of sine and cosine. So we've got cosine squared x, the quantity, that's going to be cosine squared x over sine squared x, and then plus 1. Although I look at this and I'm like, oh man, cotangent squared x, that looks like something that might be helpful to us. So maybe there's another way for me to do this. And in thinking about that, I end up with this kind of a weird idea here, which if we end up going down kind of a black hole here, I might go back and take another look. But I also notice that I can do something here with some common denominators. We'd get cosine squared x, sine squared x in the bottom. If I'm doing plus 1, that's going to be another sine squared x on top. That gives us 1. And then we end up with cosine squared x times 1 over sine squared x, which would be over sine squared x. That's the same as cotangent squared of x, and that is the reciprocal of tangent squared x. The other thing that I was thinking about would be to rewrite this as cosine squared x, and that's going to be cosecant squared x for the cotangent squared plus 1. That would be the same as cosine squared x over sine squared x, which is cotangent squared x, which is the same thing as 1 over tangent squared x. Either way, you end up doing the same types of things. Both are totally fine as a way to approach that. Okay, for this last one, looks like some common denominators again. Here we're going to have cosine x over sine x plus sine x over cosine x. When I do that, I get cosine squared x plus sine squared x over sine x cosine x. That's going to be 1 over sine x cosine x. 1 over sine x is the same as 1 over sine x is the same thing as cosecant of x, and that's times 1 over cosine x, which is the same thing we have here. That'll be it for our review.